Hello seniors, today we're going to continue with calculus. We're going to see electronic assignment number 7, where we're going to study more rules for derivatives. Up to now we have just seen one type of derivative, which is the power rule, which is the most used, but it's not the only type of derivative it exists. Today we're going to see particularly two new types of derivative, which is the derivative of e to the power of x and the derivative of natural logarithm of x. So we're going to see how to differentiate exponential functions, and how to differentiate logarithmic functions. Okay, so more rules for derivatives. The objectives for today's class are three. First, find the derivative of x to the power of n, e to the power of x, and natural logarithm of x. As I told you, we have already seen the power rule, but today we're going to see the exponent rule and the logarithmic rule. Then second objective, calculate the differentiation of a sum and a real multiple of these factors and apply the product and quotient rules for differentiation. This particular objective we're going to be covering in the next video, not for this one. We're just going to focus on this two for today. Okay, so first of all, I want to show you, in order for you to start understanding the derivative of e to the power of x, I wanted to show you how to use the calculator to evaluate the derivative of a function. Okay, so if you have your calculators with you, you can follow this explanation in order to remember each of these steps that we're going to cover today. So the first step says go to shift menu and turn the derivative on. Okay, so I'm gonna show you all of this right now in the calculator, so you should be able to see the calculator right now. So we first go to shift menu, just like if we're changing the angle, right, to from degrees to radians or radians to degrees. But before angle, you see that there's an option which says derivative. So you want to turn this on for now to see what changes when you turn that on. Okay, so then if you go to menu graph, we want to find, first of all, we want to plot the function x squared plus 4. Okay, I'm showing you this as an example. If you see, this is a quadratic function. If we graph this, well, I need to change the scale. Shift V win. Let's change this to -10 and 10. Scale 1. And then y could be from 0 to, let's say, 20. Scale 1. Okay. So you should be able to see the quadratic function right now, right? So this is a quadratic function. And what would be the derivative of this function? If you know, the derivative of this function is directly 2x, right? If we graph this function, you see that we'll have this should actually be 2 times x. There you go. If you plot this function, you see that this red line represents the gradient function of a parabola, right? And it's a straight line, right? But there's another way you can graph this function, which is doing the following. Instead of manually writing the derivative of this function, another way to do this is by clicking on option right here, and then you go to calc for calculus, and here you have an option of derivative of the function. Okay, this is another symbology of f prime of x. It's derivative of the function with respect to x. This second option represents the second derivative of a function, which we're gonna see later on. Then this third option is integral. We're gonna learn this as well for the second semester of the year. And this one is for logarithm. Okay, so we want to click on the first one, f1, in order to find the derivative of the function. Okay, so in here you may write, if you want, x squared plus 4, which is the function. Or another more simple way, in case the function is too long, is if you, let me erase this, you see that here you have y. So you want to click on f1, y, and we want to find the derivative of the first function, which is y1, right? So you click on 1. So the calculator now knows that you want to find the derivative of y1, which is x squared plus 4. And then it says x equals, and here you need to define for what value of x you want to find the derivative. In this case, we want to find the general form of the derivative, so we're just going to put x again, okay? If you want the derivative in a specific value, you're going to put x equals 1, for example, and you're going to get the value of the derivative for x equals 1. But in this case, we want the general formula, so we're writing x. So you click on enter and then draw again, and you'll see that we got the same line we got when we manually found the derivative of this function, right? So this is a way you can find the derivative of a function. Now, if you go to shift and trace, you see that here we have the function, and you have the x value and the y value for this particular point. And up here, you cannot see this clearly because we're just above the point, but here you can see the derivative, the value of the derivative of this function at this point, okay? In this point, we're at the lowest point, at the minimum point of the parabola. So the derivative or slope of the function at this point is 0, right? If I draw a tangent line through this point, I will get a horizontal line, which has slope 0. Then if I go, let's see if I can see more clearly. There you can see this clearly. If I go, for example, to this point, I get the x coordinate of the point, the y coordinate of the point, and the value of the slope, right? Which is the derivative of the function. That happens when you turn on derivative, which is the first thing we did when we turn on the calculator today. Okay, and if you see, if I go to the other function by clicking down, you would see that, it's 0. You will see that for this function, no matter the value where I am in x and y, the derivative is always 2, right? Because this is a line, and the line has a constant slope, which in this case is 2, right? So you can see that right there in the graph. Okay, so now we're going to try the following. And I'm going to erase this function, or I'm going to leave it there. But I'm going to draw now the exponential function, which is e to the power of x, okay? So let me do this, e to the power of x. So that's the function, okay? I'm going to unselect this 2 to just not see the graph. And as we did before, we're gonna plot, well, first of all, I'm gonna draw this function for you to see what it looks like. It's a normal exponential function, right? So now, as for y4, I'm gonna draw the derivative of this function of e to the power of x. So once again, we go to option, calc, first derivative. First derivative of, instead of writing e to the power of x, we can write y3, okay? And for x equals x once again. And pay attention at what will happen here. You need to look at this quickly because both lines will be drawn fast. So we get the green function and the purple function there, right? So you see that both functions are exactly the same in this case. That means that the function e to the power of x and its derivative are the same function. Okay, they are exactly the same function. That means that the derivative of e to the power of x is e to the power of x. Okay, so I'm gonna go back to the assignment right now. So from this investigation, we saw that here it says, now try to find the following function, e to the power of x. What values are displayed for g prime of x? And you see that we get exactly the same values as g of x, as the original function, okay? So from this small investigation, we get to the conclusion that the derivative of e to the power of x is e to the power of x. It's the same thing. If f of x is e to the power of x, then its derivative, it's the same thing. It's e to the power of x. Okay. And the derivative of natural logarithm of x is like this. If f of x equals natural logarithm of x, then its derivative is 1 over x. We're going to see where this comes from in just a second. Okay, so here it says, recall that y equals e to the power of x and y equals natural logarithm of x are inverses. They are inverse functions. Remember, the exponential function and logarithmic function are inverses of each other. Okay, so now I want to show you a demonstration of where the derivative of e to the power of x comes from. This is something that you don't need to know, but I'm always trying to show you this for you to understand why things are like they are, right? In this case, I want to show you why the derivative of e to the power of x is actually e to the power of x. Okay, so we're gonna begin by we're gonna find the derivative of e to the power of x by the definition of a derivative. If you remember, the definition of a derivative said that the derivative of a function is the limit when h approaches 0 of f of x plus h minus f of x over h, right? This is the definition of a derivative. So we're going to try to find the derivative of this function by using that definition. So first of all, we're going to define f of x, our function, which is e to the power of x in this case. And we're going to define f of x plus h, which would be e to the power of x plus h, right? X plus h, there. So if we want to find the derivative, we're going to apply the definition. The derivative of this function is equal to the limit when h approaches 0 of e to the power of x plus h minus e to the power of x over h. If we evaluate this function, if we replace the value of h equals 0 into this, we're going to get the following. It will be e to the power of x plus 0 minus e to the power of x over h. And this is the same as saying e to the power of x minus e to the power of x over h. Sorry, over 0. I'm replacing the value of h with 0 here and here. Okay, over 0 over 0. E to the power of x minus e to the power of x is 0 over 0. So this is an indetermination. Indetermination. Which I need to solve, right? Okay, so how do we solve this? If you remember from the properties of exponents, let me write that here. Properties of exponents. We know that if we have, for example, let me see if I have it here. Properties of exponents. Oh, it's not here. So if you remember from properties of exponents, you'll remember that if I have, for example, a to the power of, let's say, 3 plus 2, this is the same as saying a to the power of 3 times a to the power of 2, right? I can separate the exponent, the addition of the exponents into a product of the exponents, right? Of the bases to the exponents, actually. Okay, so I'm going to apply that property to this equation, and I would say that this is the same as saying limit when h approaches 0 of I'm rewriting this, okay? E to the power of x times e to the power of h minus e to the power of x divided by h, right? So you see that by doing this, I have a common factor of e to the power of x. So this would be equal to e to the power of x, sorry, the limit when h approaches 0 of e to the power of x times e to the power of h minus 1 over h. Okay? Now, since I am evaluating the limit for when h approaches 0, this e to the power of x, I can treat it as a constant value because it's not in the, I'm not evaluating that for the limit. Okay, so I can rewrite this as I can take this outside of the limit notation. So this could be rewritten as e to the power of x times the limit when h approaches 0 of e to the power of h minus 1 divided by h. Okay, so for this expression here, I'm gonna try to find graphically what is the limit of this function. Okay, so let me show you this down here. I'm gonna write we're gonna observe the graph of this function. If we plot this function, this one, e to the power of h minus 1 over h, and see what happens in the limit, we're gonna get this, okay? So using Desmos, I plotted this function. Obviously, I wrote it as x instead of h because when we plot, we need to use x as a variable instead of h. So the function I plotted is e to the power of x minus 1 over x, which is exactly this one, okay? I know that for f of 0, when x equals 0, this is an indetermination, right? Because it will be, sorry, this is not, yes, it'll be an indetermination because e to the power of, yes, I'll get over 0, right? Something divided by 0, so this would be an indetermination. Actually, it's better if we call it undefined here. Undefined. So that's exactly what we see in the graph, right? For x equals 0, the function is not defined. There's a little jump for that specific value. It is undefined. But if we evaluate the limit, remember the concept of the limit is what happens when we are approaching the function from both the left side and from the right side, right? When we approach the function from the left side to x equals 0, which is this value over here, we see that we're approaching to the value 1, okay? And when we're approaching from the right, we're also approaching to the same value, which is 1, okay? So the limit of the function when x approaches 0 is equal to 1, okay? So we already know the value of the limit, which is 1, okay? So we can replace all of this with its equivalent value, which is 1, right? So if we go down here to continue the demonstration, we're going to write this as e to the power of x times the limit when h approaches 0 of e to the power of h minus 1 over h. We know that all of this is equal to 1, right? So this is the same as saying e to the power of x times 1, which is equal to e to the power of x. So now we may conclude that, let me rewrite this just to avoid confusion here. Remember, we were finding f prime of x, right, by definition. F prime of x equals all of this, okay? So here we can also write this as f prime of x equals that, okay? So f prime of x finally is equal to what we got here, e to the power of x. So this is how we demonstrate that the derivative function of e to the power of x, which is what we were doing from the beginning, is actually e to the power of x. It's the same function, okay? So that's the demonstration for this. Okay, so with this demonstration, I want to finish the class for today because the demonstration of natural logarithm of x is a little bit longer, and I don't want to make this video too long. So I'm going to leave the second part for tomorrow, And I hope this was clear enough for you. If not, please let me know and we will clear these doubts in a future live session. See you, seniors.